Hello everyone, I'm Ayush Kaur, and I'm going to present a project named as Amazon Delivery Time Prediction. The problem I had to solve was that I had to predict delivery times for e-commerce orders based on a variety of factors such as product size, distance, traffic conditions, and shipping method. Using the provided dataset, I will pre-process, analyze, and build regression models to accurately estimate the delivery times. The final application will allow users to input relevant details and receive estimated delivery times via a user-friendly interface. This is a project summary wherein I performed univariate, bivariate, and multivariate analysis following the UBM rule with around 15 meaningful charts. And each visualization was justified, which means I justified why did I choose that visualization, the insights derived from there, and possible business impacts. Those visualizations helped us identify key trends, correlations, and anomalies. After that, I also pre-processed the data and did feature engineering, wherein I handle the missing values with suitable imputation strategies. Then I treated outliers using statistical techniques. I encoded categorical variables and textual data, underwent cleaning, normalization, and vectorization. After that, I applied feature selection. Then I split the dataset into training and testing sets and handled the imbalance using resampling techniques. After that, I developed the model wherein I developed multiple ML models using multiple different algorithms and then decided to choose which one was the best on the basis of R2 score. After that, I deployed the model and then save the final model in a pickle or job format and then reloaded and tested it on unseen data to ensure robustness. After that, our model was ready to deploy, so I deployed it on Streamlit. And the insights derived from EDA had helped us make better decisions. This is the GitHub link from where we can access the Streamlit app where the model was deployed. And it gives us accurate predictions on delivery times. So let's begin. So I imported the data and then I imported ML flow to track the ML models. And then I imported these functions to find the distance using the coordinates, both latitude and longitude coordinates. And then I passed this hour to convert the time from hour minute format to numeric format. Then I loaded data, which gave us the shape of the data. And then I cleaned the data by dropping the exact duplicates. And then I standardized categorical columns. And then I converted some numeric columns and imputed median for missing numeric columns, the values in those numeric columns. Then I did feature engineering, wherein I created a feature to find the distance between various coordinates. Also, I created time features and then I filled the null values with medians. Also, I found the day of the week if date was present using this code. And then I cleaned or standardized the traffic label and then removed the rows with missing distance, which we cannot model, or null values in essential features using this code. So after that, I did the EDA. And the first column on which I did EDA was the delivery time, of course, because that's the output. So this is the distribution of delivery time. From this histogram, we can see that the typical delivery duration is 2 to 2.5 hours, but the distribution is not perfectly normal. It is slightly right skewed, which means that some orders experienced significant delays, possibly due to traffic, weather, or long distances. Yes, this business insight could make a positive impact on the business, as understanding why some deliveries take much longer can help improve routing, traffic or weather handling, or agent assignment. Next graph I made is a box plot on the average delivery time by weather to check how weather impacts the delivery time. From here, we can see that sunny weather has the lowest delivery time, which is clearly visible here. And the median is around 100 to 110 minutes with relatively narrow spread, which means that variation doesn't happen much in delivery time in case of sunny weather. And it suggests that good road visibility speeds up deliveries. Next, in cloudy and fog, we can see it has the highest delivery times, which is obvious. The median is around 140 to 150 minutes. And it is wider spread, indicating more unpredictability in details. We can see the box here is bigger as compared to sunny weather, which shows that there's more variability in delivery times during cloudy and fog environment. And is likely due to reduced visibility and slower traffic. Next, we'll see stormy and sandstorm weather. Here. And here we can see that there are above average delays. The median is around 130 to 140 minutes. Many outliers are above 200 minutes, meaning some deliveries get severely delayed. Next, we see windy weather. Here there is moderate impact. The median is around 125 to 130 minutes, slightly higher than sunny, but better than foggy and cloudy. The last one we see is of unknown weather, which is similar to average. We can see unknown is similar to average, which means that the median here is close to 130 minutes, suggesting missing data behaves like mid-range. But we can also notice one thing that there are outliers present across all conditions, especially in extreme weathers, where deliveries can stretch up to 250 to 270 minutes, which is a lot of time. The solutions we can employ to solve these problems are, first, that we can allocate resources to assign more agents or faster vehicles like motorcycles in stormy or sandstorm conditions. Next, we can communicate the delay with customers due to bad weather. If we can estimate the delay to happen 30 to 40 minutes or longer than normal. After that, we can benchmark the performance of different agents and we can benchmark it within each weather condition to avoid unfair comparisons. Because regardless of how well an agent is, the weather would play its role. You cannot expect agents to deliver quicker in a stormy condition. So this would ensure fair benchmarking within agents. Next is the average delivery time by traffic. For that, I made another box plot, which shows the impact of traffic on delivery time. The insight I got here are traffic has a strong impact on delivery time. Deliveries under high traffic conditions take the longest on average. Median is around 150 minutes, which is visible here. High traffic has a higher delivery time, which is obvious. But there are also wider spread in that high traffic column. That's why the box here is bigger, which shows inconsistency and unpredictability. Low traffic has a tighter spread, meaning deliveries are more consistent, which is visible here. Median traffic is in between, with median times higher than low, but lower than high. Variability is also moderate here compared to high. Compared to high traffic, the variability is less in medium. Unknown traffic category behaves somewhat like medium, but with a few high outliers. Here we can see. Here they are the outliers. So after that, we can see that low traffic, however, has several outliers, which could represent special cases like bad weather, poor routes, or operational inefficiencies. Now, the solutions we can use to employ to solve these problems are that first, route optimization, traffic aware scheduling, or dynamic delivery slot allocation can reduce delays. Next is that special attention is needed for unknown traffic data to ensure accurate traffic capture that could further optimize planning. Now, next I made a scatter plot to find a relationship between distance and delivery time. And here we can see there's a straight line, which means there's weak or no correlation. The regression line is almost flat, showing little to no linear relationship between delivery distance and delivery time. This suggests that delivery time is not purely dependent on distance. There are delivery clusters, which means a large number of deliveries happen at short distances. Here we can see close to 0 km, but still show a widespread in delivery time. Some under 50 minutes, some over 250 minutes, which is visible from here. Here there's a cluster in deliveries, but there's a variation in time, a lot of variation. Some 50, some 200. So that is visible from the graph. This means even short distance deliveries can take long time, possibly due to traffic, route inefficiencies, or operational delays. In case of long distance deliveries, that means deliveries that happen at over 15,000 kilometers, these delivery times are still within the same general range of 80 to 150 minutes. This indicates that long distances are probably handled by efficient transport modes like air shipping, centralized hubs, etc., which normalize delivery times. The solutions we can use to employ to solve these problems are that distance is not the bottleneck. Optimizing last mile delivery and handling traffic delays will have a bigger impact on reducing delivery times. For short distance orders, delivery efficiency needs improvement since customers expect them to be faster. So there should not be any high variability in short distance orders. For long distance orders, maintaining efficient logistics channel is working well, but improvements in scheduling and local dispatching could further reduce time. So mainly we need to focus on short distance orders. Next, I found a scatter plot to find the correlation between agent rating versus delivery time. Here, interestingly, we can see a strong correlation is there, a strong negative correlation, which means as agent rating increases, delivery time decreases significantly. Agents rated closer to 5 to 6 tend to complete deliveries much faster, while lower rated agents often take over 200 minutes, which is not good. Performance indicator is being given to us from this graph that high agent ratings are a strong indicator of reliability and efficiency. Low rated agents, on the other hand, not only take longer, but also show greater variability in delivery times. The customer satisfaction link here is that since delivery time is a major factor in customer experience, ratings likely reflect both speed and service quality. Now at ratings around 3 to 4, we can see that delivery times are widely spread, unlike in 1 or 5 to 6 rating, which suggests inconsistent performance. At high ratings of 5 plus, performance is more consistent and clustered at lower delivery times. Now, the solutions we have to employ to solve these problems are agent rating can be used as a predictor of delivery performance in ML models. Training and mentoring low-rated agents could reduce delays and improve consistency. High-performing agents like 5 plus should be prioritized for time-sensitive or VIP deliveries. Now, the next graph I made is of agent performance by area. In this graph, we can see that urban areas have faster and more consistent deliveries, and they show the lowest median delivery time of only 100 minutes. Here. Metropolitan areas, on the other hand, show slower and more variable. Metropolitan regions have a higher median of around 130 minutes and a wider spread compared to urban, which is visible from the graph. This suggests higher unpredictability, possibly due to traffic jams, dense population, or complex routes. Semi-urban areas show the slowest deliveries. Semi-urban areas consistently show the highest delivery time of 240 minutes median. It's very high here. The box, however, is narrow, which means performance is consistently slow, not due to random variation, which gives us an insight that the delay in deliveries in semi-urban areas is because of road issues and the lack of delivery centers near the customers, not because of agent issues. Because if it would have been because of agent issues, then the spread would have been wider. But it is not wide, which means it's because of a permanent issue. So the solutions we can use to employ to solve this problem are urban deliveries are most efficient. Strategies from here could be replicated in other regions. Metropolitan areas need route optimization and traffic aware scheduling to reduce variability. Semi urban areas require infrastructure and logistics upgrades. Example, more agents, better hubs, since delays are structural rather than random in case of semi urban. Other areas may benefit from standardizing operational processes to reduce extreme outliers. Next graph I made is an efficiency metric, which checks the minutes per kilometer by vehicle type, a crucial metric. So from here we can get the insights that general efficiency levels of all vehicles have a similar median efficiency range of around 10 to 15 minutes per kilometer. This suggests that on average, different vehicle types perform comparably in terms of delivery speed per kilometer. Motorcycles and scooters but perform slightly better, which is visible from here. And they are more agile in traffic and thus slightly more efficient. But vans, however, are less efficient and also have more spread. Vans have a median close to motorcycles, but show a wider spread and more high outliers. This reflects inefficiency in congested areas or where vans cover short routes not optimized for them, as vans get trapped in traffic areas, unlike bikes or motorcycles, which can maneuver in the traffic. But bicycles give mixed performance. Bicycles show similar median efficiency, but with less variability than other vehicles. However, their outliers indicate occasional long delays, possibly due to rider fatigue, weather, or road conditions, which is shown here. Now, also we can see that there are high outliers across all vehicles. Every vehicle type has significant outliers with very high delivery times per kilometer. These could be caused by traffic jams, breakdowns, weather conditions, or route inefficiencies, rather than vehicle choice alone. The solutions to employ to solve these problems are motorcycles and scooters should be prioritized in dense, urban, or metropolitan deliveries for speed and agility. Vans should be reserved for bulk or long distance deliveries, rather than short runs, to improve efficiency. Bicycles work well for short distance, eco friendly deliveries, but operation planning must minimize conditions that cause inefficiency. Outlier analysis is important. Delays are not vehicle dependent alone, so optimizing routes, maintenance, and scheduling is equally important. Next graph I made is of category by delivery time, which gives the delivery time across all categories. The insight I found is that most product categories have similar delivery times. Categories like clothing, electronics, sports, cosmetics, toys, snacks, apparel, eh, these have delivery times clustered around 130 to 135 minutes. This suggests that delivery operations are relatively standardized across most product types. Outdoor category also shows similar delivery time trend of around 130 minutes, showing no major deviation from other retail items. Now, groceries, however, are exceptionally faster, which is evident from the graph. All other categories have similar delivery times, but grocery we can see is very less as compared to other categories. Grocery deliveries stand out with very low average delivery time of around 25 to 30 minutes. This indicates a priority service model for perishable items, possibly due to high customer expectations and competitive industry benchmarks. With the advent of quick commerce or instant delivery, the solutions we need to use to employ them are to solve the problem are we need to standardize across retail categories. Since most categories have similar delivery times, logistics operations appear well balanced. Improvement in speed will likely require system level optimizations, traffic management, routing, or agent efficiency, rather than category specific strategies. Grocery, as a strategic differentiator, is a much faster delivery for grocery highlights and operational priority and competitive strength. Like I said, with the advent of quick commerce, it's an operational priority to deliver groceries faster. Maintaining or improving this advantage is crucial since grocery customers expect quick fulfillment. Next graph I made is correlation heat map, which gives a correlation across these columns with each other. The insights I found is that agent rated correlations are that agent rating versus delivery time shows a negative correlation. Higher rated agents tend to deliver faster. Agent age versus delivery time showed moderate positive correlation, which means older agents may take slightly longer for deliveries, which is understandable. So we should give priority to younger people for long distance orders. But older people can deliver short distance orders. The location features are that store latitude and drop latitude and store longitude and drop longitude show a very strong correlation since drop off and pickup points are geographically aligned. This suggests redundancy, meaning dimensionality reduction. Example, PCA or dropping one set of coordinates might be useful. Delivery time drivers show weak correlation with distance since distance alone does not strongly affect delivery time because there are many other parameters which we had seen before like agent rating, the vehicle used, weather, and so on, which affect the delivery time. Now, there's a slight positive correlation with efficiency since less efficient routes or vehicles slightly increase delivery time. The solutions we need to employ to solve the problem are agent rating is a strong performance signal and it can be used as a feature in predictive ML models for delivery time. Location coordinates are highly correlated and can be simplified to reduce dimensionality without losing information. Distance does not strongly impact delivery time, but efficiency improves with longer distances. Urban or short trips face more delays due to traffic, while long hauls benefit from smoother routes. Peak hours induce efficiency and reduce efficiency, so scheduling, optimization, and demand balancing strategies are critical, especially during peak hours. Older agents may need additional support, example, smaller zones, better routing tools, to match younger agents' performance. In short, we can see here in this graph the agent performance across conditions, whether the weather is sunny, stormy, and so on. From this graph, we can see that traffic effect remains strong. High traffic consistently results in the highest delivery time across all weather conditions. Low traffic yields the fastest and most consistent deliveries. Now, the weather inference is that sunny weather shows lowest delivery times and least variability across all traffic conditions. Agents here perform the best. Stormy, foggy, and cloudy weather show higher median delivery times and wider spreads, meaning more uncertainty and delays. Sandstorms and windy conditions show significant delays, especially when combined with high traffic. In unknown weather case, delivery times are mid-range but inconsistent, indicating possible data quality issues. The combined effects of traffic and weather are that under high traffic and bad weather, delivery times spike dramatically, often above 200 minutes, which is evident from the graph. And under lower medium traffic and sunny weather, delivery times are shorter and most predictable, which is obvious. Now, there are also outliers in this case that weather adds greater variability to delivery times compared to traffic alone. Many outliers appear under bad weather condition, reflecting extreme delays, likely operational breakdowns, blocked roads, or safety precautions. The solutions to employ are that we need weather-aware logistics planning, rerouting, rescheduling, or adjusting expected delivery times during bad weather. The customer communication is crucial, which is that we need to proactively inform about expected delays in case of traffic plus adverse weather. Adverse weather. And also during sunny conditions, we can leverage the priority orders and we can ensure VIP or express deliveries during sunny weather, as they show the least delivery times. And it is easier for agents to deliver quicker in a sunny weather. So we can invest in better route optimization and forecasting tools, which will reduce delays caused by unpredictable weather and congestion. So this is the final data shape, and these are the information about the data, which is important after seeing all the EDA. So now we'll make an ML model. For that, we prepare dataset for modeling, and then we fill missing categorical values with unknown and do numeric imputation, and then we do train test split, where we differentiate between numeric features and categorical features, and then we do encoding of those columns, wherein we use standard scalar for numeric columns and one-hot encoder for categorical columns. Then we pre-process the data. Then we train the data on 3 different models, and one among them, which is the most optimum, would be chosen to make the final ML model. So we would first test on these 3 algorithms: linear regression, random forest, and gradient boosting, respectively. Then we did this ML flow experiment to track the models. So this is the algorithm to test the models on basis of various algorithms. So after this code, we can see that the R2 square is very low in linear regression, but it is very good in other two, especially amazing in random forest case, giving a high accuracy of 99.7%. And so we would choose the random forest case. And then we save these metrics. And then we chose the best one on the basis of root mean square error and the R2 square. And best one is random forest. So it is chosen to make our final ML model. And now to deploy the model, we install Streamlit, and then we compress the ML model for easy deployment using this code, which compresses the model by 60 to 80%. And then we import the Streamlit, and then we wrote the Streamlit application code, and wherein we input all these fields. And then we created this data frame. And then we did this process of label encoding of category columns. And we did this to predict the delivery time on this Streamlit app after the model would get deployed there with this caption later on. So this is how I did this project, and I have also shared the link of the Streamlit app, wherein we can see that the Streamlit app works very well and gives accurate predictions of delivery times with the accuracy of 99.7%. So this is the project from my side. Thank you.